Today we're going to start Chapter 13, and the rest of the term will all be dealing with trigonometry. And so trig is going to be kind of a vast study of triangles and some functions that are called periodic functions. And today we're going to look at what is a periodic function, and tomorrow we'll really relate it to the sine and cosine, which are typical trig functions to learn. So we'll start here at the top. Here is a function, a pattern. We can see that as x increases, we can see that the y value does kind of some strange things. But notice what it does is it repeats a pattern. If I look at the middle of this to the middle of this, there's one pattern. And now that pattern repeats itself. And if we have a graph that keeps repeating the same pattern over and over, we call it a periodic function. So this is a periodic function. And the period of the graph would be how long it takes for the graph to start to repeat a cycle. So for us, we could even start at this low to this low. There's one period. From this little middle to this little middle, that's a period. So we find the horizontal length of one cycle is again called the period. Now the amplitude of a periodic function is not the distance from high to low. It's half of the distance from the max to the minimum. So in other words, I showed up here, if I'm trying to find the amplitude of this graph, which I think looks like a lot of teeth, but if I'm trying to find the amplitude of this graph, I know the highest point that it reaches is 3, and the lowest point that it reaches is down here at -1. So the difference between these two is how wide the graph is, but half of that distance is the amplitude. So the amplitude of this graph would be 2. And we have kind of a little dotted line here in the center, which we will typically do when we graph trig functions. And notice that from the middle of this graph, if I go up 2 units and down 2 units, the entire graph will be within that restricted range. Okay, now, again, a cycle is just one complete pattern. When we deal with trig functions, we're going to have trig functions that are going to look different from this. They're going to end up looking something like this, that they're going to keep repeating a pattern. Okay, that's not a real great graph, but so if we look at this one, we can see that this graph, if I start here at 0, 0, goes up, does kind of a little wiggle down here, and then starts back up. And then it repeats that pattern again. So that is a periodic function because it repeats a pattern. We can see that the period of the graph is how long it takes to finish a cycle. If I start at 0, I can see at 0, 0. I can see at 4, 0, it finishes a cycle. So I have a period of 4. And its amplitude is the half of the entire length of a cycle going from top to bottom. So the highest part is 2, the lowest part is -2. So the total height to bottom is a 4-unit difference. However, half of that is the amplitude. So here's the middle of the graph right on this x-axis, and the amplitude is describing how much you go up and down from the middle. Now we want to find the period and amplitude of this graph. Now notice once again, this looks more like a typical trig function. And if I start down here at a low, I can see that my graph finishes and goes from low to low in 4 units. I could also start it over here at a high, and it starts at a high at -2 and then starts to repeat here at 2. So again, I'm going to get that my period is 4. Now my amplitude, I have to go, the highest point it is on the graph is 2, and the lowest that it goes is -1, so that distance is 3 units, and half of that is my amplitude. And we'll be using that type of skill over and over when we graph sine and cosine functions shortly. Now, on the back, I don't think we need to do too much with this because I think it's pretty self-explanatory. I'm not going to read all this. You can read this, and just for time's sake, I'll let you read this. You can even turn the video off and read that a second. But I basically am looking at how big one cycle is, and I can see that one cycle, if I start the graph here to here, that distance is going to be my period. Also, this graph is scaled so that each of the little tick marks is actually 1 over 360 of a second, so 1/360th of a second for each of these squares. And so if I count from either from high to high, or go from low to low, or start kind of right here at a middle to here, I can see that there are 6 little tick marks as how long it takes for this graph to finish a cycle. Each one of those tick marks is actually, again, 1/360th of a second. So I have 6 of those. So my period, or how long it takes to finish a cycle, is 1/60th of a second. And my amplitude, the highest it goes, is up here to 120, down to a low of negative 120. So I am going to have the whole height to the base is 240 units. However, half of that is my amplitude. So the basic idea for that amplitude is wherever the middle of the graph is, which in this case is going to be this x-axis, how far I go up or down is what my amplitude is. And amplitude is always considered a positive value, by the way, as well. And again, this last one, I asked you to graph a graph that has a characteristic that it has a period this long, and it has an amplitude of 2 volts. So it's to go up 2 and down 2 from a middle. I just chose to graph my graph, so I started here at 0, 0, and I went up 2 units and down 2 units. You can see I spread it out a little bit. And I knew that my graph had to finish a cycle in 0.004. We will learn something important for a graph like this, and this is an actual graph of a sinusoidal or a sine function, really. We will find something kind of interesting. If a graph is going to start here and then finish an entire wave, every fourth of this, so in this case every 0.001, the graph is going to do something kind of unique. Like if I start the graph here, a fourth of the wave later will go to a high, fourth of the wave later to a middle, fourth of the wave later to a low, fourth of a wave later it will go back up to a middle. Or if I started at a high, fourth of a wave it would go to a middle, fourth of the wave to a low, fourth of a wave to a middle, fourth of a wave to a high. So we're going to find that a quarter of the period is actually a real important feature to look for. That's why I scaled my graph by 0.001s. Now, we're going to change gear, and this is going to deal with information from page 717. So, and I didn't add this into the notes, so you can just do this on your paper. So this is dealing with page 717, and it will look kind of odd that we're looking at this right now, but we're going to look at 2 special triangles. One of them is going to be the 30, 60, 90 triangle, and that will be dealing with degrees. And the other one is going to be the 45, 45, 90 triangle. And again, those will be in degrees. And if we have a 30, 60, 90 triangle, we can prove, and I'll probably do it in class, that if I have a triangle like this, and I measure it and I get this to be 30 degrees, and I get this to be 60 degrees, and obviously that's going to be the 90 degrees, that there is a special relationship that you dealt with in geometry that we want to review. And first of all, if we have, I'm going to let this short leg, and we can definitely see that this is the shortest side of this triangle because it's opposite the smaller angle. And so the hypotenuse is always the longest side, and we know that of these 2 legs, this has to be the short leg, and I'm going to call that leg little s. Now, the unique characteristic that we have if we have a 30, 60, 90 triangle is, and let me show you this just real quickly here, because if I plopped another 30, 60, 90 triangle right next to this and had this be 30 degrees here and 60 degrees here, notice that this triangle would end up being an equilateral triangle. It would have all of these sides would be the same, all these angles would be the same, 60 degrees, 60 degrees, 60 degrees. And so if this side is of length s, this side would be of length s, which means that this length has to be the same as this length. So this side would be 2s. And if we use Pythagorean theorem and do leg squared plus leg squared equals hypotenuse squared, we can prove that this leg right here has to be square root of 3 times longer than s. And I'm going to erase that other little triangle so he doesn't get in the way. But that's how basically we prove that that relationship holds true. So a little bit of geometry, and so now we have that relationship. So if I look at this, for any type of 30, 60, 90 triangle, we are always going to have the short leg being half the length of the hypotenuse. Or if we know the short leg, we double it and we get the hypotenuse. And if we're comparing short leg and long leg, we would take the short leg times the square root of 3 and get this value. So for instance, if I gave you this 30, 60, 90 triangle, and I said, here's your 60-degree angle, 30-degree angle, and if I said this side is 4 units long, then we would know that this side must then be 2 units long, because there's always a 1 to 2 ratio here. And once we know the short leg, we know we take the long leg and find it by taking the short leg times the square root of 3. Now, what if I gave you the long leg? So if I have this be my 60-degree angle, this my 30-degree angle, and if I told you that this long leg on the right triangle is equivalent to 8 inches, and I said, how long are these other two sides? Well, if I know this, I know I have to take this side and double it to get the hypotenuse, because I know that geometric relationship holds true. And if I know this side, I multiply by the square root of 3 to get this one. So if I know this side, I have to divide it by the square root of 3 to get this one. So this number must be 8 divided by the square root of 3. Now, that is not rational. I would need to simplify that. So this shorter leg, I'm going to multiply top and bottom by the square root of 3. And so this length of this short leg would be 8 square root of 3 over 3. And the hypotenuse has to be twice as long. Multiply that by 2, and I'd find that this is 16 times the square root of 3 over 3. So it's nice when you have this relationship is to write down a general triangle so that you remember the relationship. And again, obviously this has to be the shortest leg. And remember the hypotenuse is twice as long. And short leg to long leg, take short times the square root of 3. Now for the 45, 45, 90 triangle, that's an isosceles triangle. So if we remember that, it has to be an isosceles triangle, because if we have these two angles being the same, we can prove that these two sides have to be the same length. And so if I label each of these sides and just call them S here, we could use Pythagorean theorem to prove that this hypotenuse has to be square root of 2 times longer. So leg squared plus leg squared has to equal this hypotenuse squared. And do a little bit of algebra and we'll get this. So this is a real nice relationship. If I gave you this triangle and I said it's a 45, 45, 90 triangle, if I give you a leg, like right here, if I say that this leg is 14 inches long, then obviously this has to be 14 inches long. And then in a 45, 45, 90 triangle, the hypotenuse is always square root of 2 times longer. So this would have to be 14 times the square root of 2. And on the other hand, if I gave you a 45, 45, 90 triangle, and I tell you the hypotenuse, and I say the hypotenuse is 5 inches long, well, we know if we know this leg, it's the same as this leg, and multiply this leg by square root of 2 and we get this. So to go the opposite direction, this has to be 5 divided by the square root of 2, which once again we will rationalize. So I'll multiply top and bottom by the square root of 2. And so this leg would have to be 5 times the square root of 2 over 2 inches long, and so does this one. Okay, so you'll have a little bit of practice today dealing with periodic functions, as well as this little review of the special triangle, the 45, 45, 90 triangle and the 30, 60, 90 triangle. So now you're ready to work.